in question 4 we have a bit of refraction going on, and first of all it wants to know what the speed of light is within this glass prism, and the key to that is this relationship, which is on your datasheet, which tells us that the refractive index of a substance is given by the speed of light in a vacuum divided by the speed of light within that substance. And since it gives us the value for the refractive index in the question, okay, so we've got that n is equal to 1.5, so that makes it very easy because we can just rearrange that equation to get that C of S is equal to C over n, which is 3.00 times 10 to the 8, that's on your data sheet, remember the speed of light in a vacuum, divided by 1.5, which is 2.00 times 10 to the 8 meters per second, is the answer. The next thing it wants us to find is the value of this angle theta, which is the angle of incidence, in other words the angle between the normal here and the incident ray coming in. So to do that, we're going to use this relationship, which again is on your data sheet. So the key to that is that we've got two media here, we've got the glass and we've got the air. So we can rewrite that as n of the air, which, because that's what's out here, times sine theta, which is the angle of incidence that we want to find, is equal to n in the glass times sine of the angle of refraction, which is 15 degrees. Okay, so that's just substituting in 1 being the air and 2 being the glass. So saying the refractive index of the air times sine of that angle is equal to the refractive index of the glass times sine of the angle of refraction, which is 15 degrees. And so we can rearrange that to get that sine theta is equal to the refractive index of the glass times sine 15 degrees divided by the refractive index of the air. And all those numbers are accessible because the refractive index of the glass it gives us in the question is 1.5 times sine of 15 degrees, which we can get from your calculator, and the refractive index of the air, remember, is 1 because the velocity of light in air is almost, not quite, but almost, and certainly at the level of accuracy we're working to, identical to the velocity of light in a vacuum. So the refractive index of air is 1. So we can just plug that number into there, so it's just 1.5 sine 15 degrees comes to 0.3882, and therefore theta is the inverse sine of that number, which is 22.8 degrees, or 23 degrees to two significant figures. In part 2, it wants us to find the refractive index of this liquid layer here. So what we've got there is again refraction at a boundary. So we've got, this time our incident ray is this ray coming down here, and then the refracted ray has been bent all the way up through 90 degrees. Okay, so we've got a 90-degree angle there because it's emerging right there along that layer. So we've got a 90-degree angle of refraction there. So again, we're going to use this relationship. So we've got n glass sine theta in the glass is equal to n liquid times sine theta in the liquid. So we know what n in the glass is because it tells us in the question, but we've got to find what this angle is, because that's the angle of the incident ray coming in there, and that's the number we need for there. So we're going to have to use our ideas about triangles to get that. And then we know what the sine of that angle is because that's 90 degrees, so that's easy. And so we're going to be able to do it like that. So first job is to find what this angle here is. So we can do that because we know that it tells us in the question that this is a 15-degree angle, and of course this is a right angle because that's the angle between the normal and the interface layer. So that total angle here is 105 degrees. Okay, 90 plus 15. So if we think about this triangle here, we've got 105 plus 45 makes 150, and so this angle must be 30 degrees, so that they add up to 180. So we get that angle is 30 degrees. And because that's a right angle here, if that's 30 degrees, then this angle, which is the one we want, is 60 degrees. Okay, so now we're in business. So the first job is that we can rearrange that to get that n in the liquid is equal to n in the glass sine theta in the glass divided by sine of theta in the liquid, which is equal to 1.5, so refractive index of the glass, times sine of 60 degrees, because that's the angle of incidence, divided by the refracted angle, which is not, the sine of the refracted angle, so divided by sine of 90 degrees. But of course the sine of 90 degrees is just 1, so that's equal to 1.5 sine 60 degrees. That comes to 1.3. Okay, and you can always check that makes sense. First of all, if it's a refractive index, it should be a little bit bigger than 1, which it is, so that looks like a sensible number. But also, because this ray was bent further away from the normal, you know that it's moved into a region of lower refractive index, and so it makes sense that that number 1.3 is lower than the 1.5 in the glass. So again, you can just do a little bit of quality control and check that those numbers you're getting make sense.